Hi, folks. We've been talking about ionic bonding, and the product of ionic bonding are ionic compounds. And I want to spend a few minutes talking about the properties of these ionic compounds. One of the ways that we make sense of chemistry and a lot of complicated data is that we put things in categories. And all of these ionic compounds have some properties in common. So let's talk about the things that make these ionic compounds similar. This broad group are known as salts. Salts are a metal ion plus a non-metal ion. Now, when you and I think of table salt, I typically think of the sodium chloride that I put on my French fries. But in chemistry, we're talking about this broad range of ionic compounds with positive, negative ions that are bonded together. They can be of a variety of different metals, non-metals. Remember, the halogens are named for being salt formers, but they do not have to include halogens. It is just a generic name for this large group of compounds. Ionic compounds often dissolve in water. Matter of fact, that dissolving in water is a big property of many of these. Not always do they dissolve in water, but many of them do. Couple examples we've talked about in the past is like saline solution that is used in an IV. We've talked about copper sulfate solutions and things like that. Why is this important? Many of you are going into a health profession, and the human body is one big gooey thing full of a lot of liquid solutions. A lot of the chemistry of life occurs in solution, in water, and a lot of the ions that you and I need for living and transporting energy from place to place occurs because of these ionic compounds. The big exception, of course, are the alkali earth metals and some transition metals, also referred to at times as heavy metals, are not terribly soluble, but most of these ionic BCs are going to be soluble. This is a bit of vocabulary that I want you to know. The smallest unit of an ionically bonded substance is not called a molecule. It's actually referred to as a formula unit. So why don't you call a small piece of sodium chloride a sodium chloride molecule? And I apologize right off the bat because I probably have used that term and will use it again in the future. Because molecule is just easy to say, and we're used to referring to groups of atoms as molecules. But the correct term is formula unit. Why differentiate? Why is there this separate name? Well, it has to do with this solubility and the fact that when you put an ionic compound into water, it tends to break back up into ions. Remember, we mentioned the fact that ions have different properties than their constituent parts. Sodium is this silver metal that is dangerous when you get it wet. Chlorine is a poisonous gas. You make sodium chloride, and it is this bonded positive and negative pair of ions that taste salty and tastes good on potato chips. Well, when this is put in water, you actually have the negative chlorines and the positive sodiums that can be swimming around in the same glass of water if you put salt in water for some reason. And you taste that saltiness, but they don't necessarily have to be bonded to the same water molecule. So they can actually break back up into the constituent parts and don't have to be cuddled up next to each other and still be salt, but they are not forever bonded like a molecule is. And hence, because of the wacky way they act as ions, they are called formula units and not molecules. Ionic compounds at room temperature are solids. And what does that tell us about ionic compounds? Well, it tells us they have really, really high melting temperature. I picked two common things, table salt and common rust. Table salt has a melting temperature of about 1,500 degrees Fahrenheit, rust of 2,500 degrees Fahrenheit. Most ovens go up to about 500 degrees Fahrenheit if your common oven. If you put table salt into a frying pan and you try to melt it, it's not going to happen. This is an indicator of very, very, very strong bonds. These ionic bonds are really, really strong because melting temperature is a huge indicator of how strong one particle is attached to another particle. In nature, we're going to find these ionic compounds in rocks and minerals. Limestone, calcium carbonate, iron sulfide, which is fool's gold, or pyrite, fluorite. A lot of the things you're going to find out as the rocks and inside of soil and dirt, those are going to be your ionically bonded compounds. These are going to be the minerals that you're going to find lying in the dirt on the surface of the earth and within the earth itself. So these are not so much the compounds that are going to make up butterflies and bunny rabbits in great abundance. These are going to be the trace elements and minerals essential for life. If you take a vitamin and mineral supplement, inside of them, there is going to be vitamins. Now, these vitamins are going to be organic molecules that you have to get from plants and fruits and vegetables. That's going to be the source of those vitamins. But if you want to get minerals, the calcium, the phosphorus, iodine, magnesium, zinc, selenium, copper, manganese, chromium, where are those going to probably be sourced for your vitamin minerals? Those are going to be ionic salts. And that is what is typically going to be the source for some sort of a vitamin and mineral supplement. Totally different kinds of molecules. Why are they both in there? Because the human body needs both. These ionic compounds, when we find them allowed to build on their own very slowly in caves and inside the earth, they form beautiful regular crystalline structures. And they make beautiful things. This is a picture of a piece of ruby. This is an emerald. This is a garnet. This is plain old ordinary sodium chloride, fool's gold here, collection of everything from fluorite to amethyst. And these cool structures, the geometry, this was not made by man. Nobody came around and said, hey, let's cut it into cool shapes. These just were created by the atoms forming in the shapes they wanted to form in. And these have given chemists clues to how the atoms are actually bonded in these regular ionic structures. Another property of ionic compounds, because they do tend to dissolve in water, and this is a common test for the presence of ions in solution, is we use a tester, an ion tester, a little electric gizmo with a light bulb on it, to see if there are ions in solution. And I'm going to ask you to watch another video after this one that shows a variety of different solutions being tested to see if they conduct electricity. And if they conduct electricity, that means they contain ions. And one of the most interesting things is plain water, plain old ordinary distilled perfect H2O does not conduct electricity, but it's the ions in the water that conducts that electricity, and that's the stuff that's dangerous. So please be careful. You are not a pampered little princess. You do not take a bath in distilled water. Be very, very careful and keep those electrical appliances away from your tub and your rubber ducky. All right, we will see you a later time. Bye-bye.